Earth sits a mere 150 million kilometres from the Sun. Not too hot, not too cold, with surface temperatures ranging from -88 to +58 degrees Celsius. This Goldilocks location has created a stability of climate that, despite the best efforts of ice ages and impacts, has allowed life to maintain an unbroken chain for nearly 4 billion years. And yet we know for certain that it cannot last. Our Sun, like every star in the universe, is far from static. Stars have life cycles of their own, and eventually the hydrogen fuel that powers the nuclear reactions within a star will begin to run out, and the star will enter the final phases of its lifetime. It will expand, cool, and change colour to become a red giant. Small stars, like our Sun, will undergo a relatively peaceful and beautiful death, which will see it pass through a planetary nebula phase to become a white dwarf, which will cool down over time to leave a brown dwarf. Life on Earth has prospered through our Sun's middle years, but these optimum conditions are waning. At first the changes will be invisible, but 1 billion years from now they will be obvious to any life forms left on the planet. An immense sun filling the sky will warm and transform itself and the Earth that it shines upon. The Sun is both the giver and the taker of life on our planet. It is one of the great paradoxes of the universe that as the life of a star like ours begins to wane, its size and luminosity will increase. A rise in luminosity of just 10% will see the average surface temperature on Earth rise to 47 degrees Celsius instead of the 15 degrees Celsius that it is today. The effect of this rise in temperature manifests in a lifting of vast amounts of water vapour from the oceans into the atmosphere, creating a greenhouse effect that could quickly and rapidly run out of control, evaporating the oceans and sending the surface temperature skyrocketing. Astrobiologist David Grinspoon explains. The greenhouse effect is the name we give to the physical process by which planets heat up through the interaction of their atmospheres and solar radiation. Basically, solar radiation comes in what we call the visible wavelengths. Primarily, they're wavelengths that we can see, and most atmospheric gases are very transparent to visible radiation. So light from the Sun comes through pretty much unimpeded by an atmosphere and reaches the surface of a planet. Then the surface of the planet re-radiates that radiation in infrared, because planets are much cooler than the Sun. And that means they radiate at much longer wavelengths, what we call infrared or heat radiation. That infrared radiation doesn't make it through an atmosphere so easily. Some of the atmospheric gases, the ones we call greenhouse gases, block infrared radiation, and so therefore the more of those greenhouse gases that are in a planet's atmosphere, the harder it is for that surface radiation to make it back out into space, and the more that planet will heat up. Estimates of the time scale that will see our oceans disappear vary massively, and are heavily influenced by a multitude of factors. But few are in doubt that by the time our planet reaches its 8 billionth birthday, in 3.5 billion years' time, the end will be in sight. With temperatures heading above 1,000 degrees, life will have long disappeared from a surface that is beginning to melt under the burning sun. Moving even further into the future, the outlook becomes bleaker. As the Sun enters old age, it will grow into a red giant, engulfing the Earth within its expanding atmosphere. Moonless, lifeless, and perhaps reduced to its inner core, our planet and the civilizations it once harboured will be nothing but a distant memory, etched in the atoms that made us all, as they are dispersed amongst the cosmos. For planet Earth, the clock is ticking, and time is slowly running out. But ours is far from the only world to enjoy its moment in the sun. Across the history of our solar system, stretching deep into its ancient past and reaching far into its future, we see stories of worlds in a constant battle with our ever-changing star. Close in, ancient worlds such as Mercury, which long ago lost their fight with the sun, are taunted by views of Earth and what might have been. Further out and even hotter, Venus circles, shrouded in a choking cloak of cloud, and even further beyond the Earth, Mars sits cold and barren. Beyond these planets, frozen worlds await, huddled in perpetual hibernation, anticipating the moment when the warmth of the sun reaches out far enough, with sufficient heat, to trigger a first spring. On that day, mountains of ice will melt, rivers of water will flow, and where there was once only bleakness, in the distant future on planets once frozen and lifeless, we might find a place that looks very much like home. The story of our solar system is not as we once thought it, eternal and unchanging. Instead, it is a place of endless transformation. It is a narrative that repeats itself with a predictable rhythm. As one world passes, another comes into the light. Only one planet has maintained stability for almost the entire life of the solar system. The Earth has remained habitable for at least 4 billion years, while change has played out all around it. What makes the Earth so lucky compared to all of its terrestrial siblings? To answer that question, we need to look not just at our planet, but at the whole of the solar system, going right back to the very beginning. In the beginning. For the first few million years after its birth, there were no terrestrial worlds to see the sun rise, and there were no days, no nights, no circular tracks around it. Instead, surrounding our infant star was a vast cloud of dust and gas. A tiny fraction of the material left over from the sun's formation. This swirling cloud would one day coalesce to form the various planets of the solar system, and many other smaller bodies. But at this time, 4.7 billion years ago, there was nothing but tiny specks of dust reflecting back the light of our slowly growing star. Only time, vast amounts of empty time, would allow enough of this gas and dust to catch and cluster, randomly forming the smallest of seeds. Most of these seeds would hardly get the chance to grow at all, smashed apart and returned to the immense swirl of dust from whence they arose. Just a few would grow big enough and survive long enough to capture and condense more of the cloud, slowly increasing their mass and density. We still do not fully understand the process by which grains of dust no thicker than a human hair can amass to become rocky objects the size of a car, and as yet no model exists to explain this part of the evolution of a planet. But what we do know is that once that disk of gas and dust becomes populated with clumps of rock that make it past the meter-sized barrier, a powerful force comes into play to propel the process forward. These newly formed planetesimals are big enough to allow the great sculpting force of gravity to draw the clumps together, growing to sizes of over 1 kilometre in length. Swirling around the sun, thousands upon thousands of these objects live and die, colliding and coalescing under the increasing gravitational forces of attraction, until eventually just a few emerge as planetary embryos, moon-sized bodies known as protoplanets. In the last violent stages of the process of planetary birth, these protoplanets swirl around in crowded orbits, and many are destroyed, returned to the dust of their origins. But occasionally, when a collision brings 2 or more of these giant objects together, the size of this mass of rock becomes big enough for gravity to pull it in from all sides, creating a sphere of newly formed rock, a new world. In that moment, a planet is born. Each of the terrestrial planets in our solar system was born this way. They are the survivors of a process that destroys far more worlds than it ever creates, and which left just 4 rocky planets remaining, starting closest to the Sun with Mercury, then Venus, Earth, and finally, farthest out, the cold and dead world of Mars. Today, these 4 worlds all look vastly different, and yet all were created the same way, made up of the same ingredients and orbiting the same star. So why have they ended up so distinct from each other and with such starkly different environments? And what makes this place, the Earth, so unique, the only one of the rocks that has blossomed with life? To understand, we have to look deep into the past of our solar system, to explore the unique history of each of the planets by means of amazing feats of human engineering across billions of miles, and into environments of unknown and unimaginable extremes. Exploring Mercury. Getting to the smallest planet in the solar system is anything but easy. Skirting past the Sun at a distance of just 46 million kilometers at the closest point in its orbit, Mercury is a planet that is not only held deep in the gravitational grip of our massive star, but is also moving at an average orbital speed of 48 kilometers per second, by far the fastest orbiting planet in the solar system, and far outpacing the Earth's more leisurely 30 kilometers per second. It needs to whip around this quickly, otherwise it would have fallen into the Sun's embrace long ago. But the combination of its speed and position make it a planet that's immensely difficult to get close to, and even harder to get into orbit around. In order to do so, you have to travel fast enough to catch up with Mercury, but not so fast that you cannot somehow slow down to prevent a headlong descent into the Sun. And that challenge has meant that until relatively recently, it was the least explored of all the terrestrial planets. For many decades, our first and only close-up glimpse of the innermost rock orbiting the Sun came from the Mariner 10 spacecraft, when on 3 separate occasions in 1974 and 1975, it briefly flew past Mercury. This was the first spacecraft to use another planet to slingshot itself into a different flight path, using a flyby of Venus to bend its trajectory, to allow it to enter an orbit that would bring it near enough to Mercury to photograph it close up. Clad in protection to ensure it could survive the intense solar radiation and immense extremes of temperature, Mariner 10 was able to send back the first detailed images of Mercury as it flew past at just over 200 miles above its surface. It passed by the same sunlit side of Mercury each time, so it was only able to map 40 to 45% of Mercury's surface. The spacecraft took over 2,800 photos, which gave us never-before-seen views of the planet's cratered moon-like surface, a surface that we had never previously been able to fully resolve through Earth-based observation. Despite the beauty of the pictures taken, it wasn't the images from Mariner 10 that really surprised us. It was the data the probe collected relating to Mercury's geology, which pointed to a much more surprising history of the planet than had previously been imagined. Mercury, it seemed, was far from being just a scorched husk. Mariner was able to sense the remains of an atmosphere, consisting primarily of helium, as well as a magnetic field and a large iron-rich core, opening a mystery that would remain unexplored for another 30 years. As it flew past Mercury for the last time on the 16th of March 1975, the transmitters were switched off and its contact with Earth silenced. Mission completed, Mariner 10 began a lonely orbit of the Sun that, as far as we know, continues to this day. At first sight, many things about Mercury simply don't make sense. During its 88-day orbit around the Sun, it travels in a lopsided elliptical orbit, which means it can be as far away from the Sun as 70 million kilometers, but occasionally as close as 46 million kilometers. This is by far the most irregular of orbits of all the planets. But it is not the end of Mercury's oddity. Temperatures at midday can rise to 430 degrees Celsius on the surface, but at night, because it's a small planet and it has no atmosphere, temperatures fall to minus 170 degrees, giving it the greatest temperature swing of any known body in the solar system. Its rotation is also unusual, gravitationally locked to the Sun in what is known as a 3-to-2 spin-orbital resonance. This means the planet spins precisely 3 times on its axis for every 2 orbits, which in turn means that its day is twice as long as its year. In effect, you could be travelling over its surface at walking pace and keep the sun at the same point in the sky as you strolled through eternal twilight. As planetary scientist Nancy Chabot explains, a day on Mercury is not like a day on Earth. It has a very unusual orbit. It has to go around the sun twice to have one complete solar day on the planet, where the sun goes from directly overhead to directly overhead, and this actually takes 176 Earth days. Because of the planet's orbit, there are places on the Mercurian surface where a hypothetical observer would be able to see the 2.5 times larger in the sky sun appear to rise and set twice during one Mercurian day. It rises, then arcs across the sky, stops, moves back towards the rising horizon, stops again, and finally restarts its journey towards the setting horizon. Most of Mercury's anomalies can be explained by the orbital mechanics of its journey around the Sun, except, that is, for the odd elliptical orbit that takes it on such an oval-shaped, elongated course. This irregularity has puzzled astronomers for centuries, and hints at an ancient planet that was very different from the Mercury we see today. To truly begin to understand Mercury's history, we had to wait nearly 40 years before we could return to her. On the 18th of March 2011, NASA's Messenger spacecraft became the first to enter Mercury's orbit. And over the next 4 years, it succeeded in not only photographing 100% of the planet's surface, but also collecting extensive data on its geology. But before any of this could happen, Messenger had to take perhaps the most circuitous route in the history of our exploration of the solar system. Just passing close to Mercury to take a few snaps, as Mariner 10 did, is hard enough. But actually entering into its orbit was thought to be either too difficult to achieve or too costly to execute, as cosmochemist on the Messenger mission Larry Nittler explained. There are two major challenges to getting a spacecraft into orbit around Mercury: gravity and money. When you go from Earth to Mercury, you're falling into the gravitational well of the Sun, which makes you accelerate faster and faster as you get closer. And if you were to go straight from Earth to Mercury, this means that you would basically just zip right by the planet, or you would need to bring an incredible amount of fuel to put the brakes on, more than you could actually afford. A number of missions never made it further than pencil and paper, while others floundered and failed at the proposal stage. It was only when Chen-Wan Yen, a NASA engineer from the Jet Propulsion Laboratory, JPL, provided a trajectory that could not only get a craft into orbit, but could do it at an estimated bargain bucket cost of $280 million, that the Messenger mission could really begin to take flight. Taking off from Cape Canaveral on the 3rd of August 2004, Messenger began a 6-year, 7-month, 16-day journey to Mercury that would take it on a 7.9 billion kilometre trajectory before it entered into orbit around the smallest of all the planets. To arrive at Mercury with the right speed and on the right course would require a complex route that would entail a number of gravity-assist manoeuvres around the Earth, Venus, and Mercury itself to reduce the speed of the craft relative to Mercury. So, combined with the brief firing of its large rocket engine to finally insert it into orbit, this mission profile allowed Messenger to complete its voyage without the need to carry the vast reserves of fuel required to slow its passage through the firing of rockets. This design made the craft lighter and cheaper, but ultimately much slower. Almost 7 years was a long time to wait for the team patiently charting its progress across the stars. Larry Nittler described Messenger's course as sneaking up on Mercury by taking a 7-year journey, flying around the Sun many times, doing multiple flybys around Mercury and Venus, and each time transferring some of the craft's speed and energy to the planet, so it could slow down, so that when we finally got to Mercury after 7 years, we were able to fire our engine just a little bit to slow down even more and get captured by the weak gravitational field of the planet. Appropriately, when Messenger finally entered into Mercury's orbit at 0045 UTC on the 18th of March 2011, the path it settled into was highly elliptical. This orbit took it on a 12-hourly cycle from 200 kilometers above the planet's surface to 10,000 kilometers away from it. It may seem like an odd orbit for a craft with the singular aim of getting as close to Mercury as possible, but this was an essential part of the design of the mission, vital to protect Messenger from the fierce heat radiated by the scorching hot surface of Mercury. The sunlight reflected from the surface is so powerful, it would have literally melted the solder holding the spacecraft together if it wasn't given time to cool down between its closest approaches to the planet. Protected by an enormous ceramic solar shield and its eccentric orbit, Messenger could begin its work. For 2 years, the spacecraft mapped pretty much every bit of the surface of Mercury, and the images beamed back to Earth revealed a planet that's been in the firing line for billions of years. Too small to hold on to an atmosphere that might protect it from meteorites, and lacking any processes to recycle old terrain, Mercury's ancient surface is the most cratered place in the solar system. Mapping Mercury. The Mariner 10 mission had enabled scientists to see about half of the planet, so the first real glimpses into the terrain of Mercury came from the flybys of Messenger. As planetary scientist Nancy Chabot explains, before Messenger, we had only seen 45% of the planet, and we saw some stuff during the flybys before we went into orbit. But after orbiting the planet, we've now mapped 100% of the planet and seen nearly everywhere. There are some permanently shadowed regions which are still mysterious, but after mapping the full planet, we have a good idea of what the surface looks like, and craters are absolutely a dominant landform. This planet has been sitting there for billions of years and been hit over and over, and it hasn't had a lot of processes to destroy those craters. Amongst the thousands upon thousands of craters on Mercury, the largest by far is Caloris Planitia, a lowland basin 1,525 kilometers in diameter that is thought to have formed in the early years of the solar system around 3.9 billion years ago. It was first spotted as Mariner 10 sped past in 1974, but due to the trajectory and timing of the craft, only half of it was lit, so the full character of this crater remained a mystery for another 30 years, until Messenger could photograph it in all of its glory. Taking one of its very first photos, Messenger revealed Caloris to be bigger than had been previously estimated, encircled by a range of mountains rising 2 kilometers from the Mercurian surface, whose peaks create a 1,000-kilometer boundary around the lava plains within. On the other side of the mountains, the vast amount of material that was lifted from the planet's surface at the moment of impact formed a series of concentric rings around the basin, stretching over 1,000 kilometers from its edge. The collision that created Caloris hit Mercury with such force that it also had more global consequences. Messenger photographed in great detail an area named, in the not particularly scientific vernacular, the weird terrain, a region at the planet's diametrically opposite point, the antipode to Caloris. This area of strange geological formations, distinct from the rest of the surrounding terrain, was likely created by the seismic shock wave of the Caloris impact, reverberating through the whole of the planet. Right up until the end of its mission in 2015, Messenger continued to uncover many of Mercury's secrets, including a few very particular surprises. Using a combination of photography, spectroscopy, and laser topography, Messenger revealed tantalizing evidence that even this close to the Sun, water ice can exist on the surface of a planet. Even though the Sun blasts much of Mercury's surface, the tilt of its rotational axis is almost zero, so there are craters and features around the planet's poles that never see direct sunlight. Combined with the lack of atmosphere, these regions are forever exposed to the freezing temperatures of space, and it's in this environment that Messenger was able to record the clear signature of water ice. Here, in the eternal night of a polar crater, it's cold enough for ice to survive for millions of years, just meters away from the savage ferocity of the sun's light. However, Messenger's most startling discovery was still to come. The mission objectives had been developed to explore the deep history of Mercury and provide data to test against our theories of the formation and early life of the planet. Messenger was equipped with a collection of spectrometers designed to analyze the composition of Mercury at different depths. The Messenger team had worked on a detailed set of predictions outlining the chemistry of the planet. But as the spacecraft began to sniff at the Mercurian surface, it soon became clear that our assumptions had not been quite right. As the gamma-ray and X-ray spectrometers analyzed the elements on Mercury's surface, they began to measure the unexpected characteristic signature of a number of elements such as phosphorus, potassium, and sulfur, at much higher levels than they were expecting. Up to this point, the working hypothesis had been that during the formation of Mercury and all the rocky planets, as the rock condensed and combined to form the planet, the heavier elements like iron would sink towards the center, forming the bulk of the core, while the lighter elements, such as phosphorus and sulfur, would remain near the surface. These more volatile elements would then be expected to be stripped away from the surface, particularly on a planet like Mercury, which is so close to the Sun. And yet the Messenger data confirmed high levels of potassium, and sulfur was detected at 10 times the abundance of the element on Earth or the Moon. Both are volatile elements, easily vaporized, and when this close to the Sun, they simply should not have survived the planet's birth. On top of that, the Messenger data confirmed what we had long suspected about the structure of Mercury, that it is the densest of all the planets, with a massive iron core making up 75% of the planet's radius, compared to just over 50% here on Earth. The core creates a strange lopsided magnetic field, indicating that the internal dynamics of the planet are different to anything we have seen before. All of this adds up to making Mercury something of a mystery, as nothing quite accords. The eccentric orbit, the abundance of volatile elements on the surface, and the oversized iron core all point to the planet having a history far more complex than was first imagined. And the only explanation to make sense of the Messenger data is that Mercury was not born in its current sun-scorched position. It has long been supposedly known that the orbits of the planets are eternal, stable loops that sustain the structure of the solar system in an endless rhythm. But everything we are learning now suggests that this is far from the whole story. A secret history. Mercury, like all 4 of the rocky siblings, was formed of molten rock. A few million years later, as the young planet began to cool, its crust solidified, and its journey around the Sun transformed from being part of a swirling cloud into a clearly defined passage, an orbit. The path the infant Mercury travelled, however, was most probably far removed from the course it now holds. The young Mercury was born not as the closest planet to the Sun, but at a much greater distance, far beyond the orbit of Venus, beyond Earth, perhaps even beyond Mars. This was a planet that came into being in the mildest region of the solar system. It was far enough away from the Sun to allow volatile elements like sulfur, potassium, and phosphorus to be folded into its first rocks without being vaporized away by the heat of the Sun, but maybe near enough for its surface to be warmed, perhaps even just the right amount for liquid water to settle on its surface. This may well have been a planet big enough to hold an atmosphere, a watery world upon which all the ingredients of life could well have existed. Mercury, it seems, really did have its own moment in the Sun, but these hopeful beginnings were not to last. Today, it's hard to imagine the planets in any orbit other than our night sky. They feel eternal, permanent, and so it's natural to think of the solar system as a piece of celestial clockwork, a mechanism running with perpetual and unchanging precision, marking out the passage of time. In time frames that we can comprehend, days, weeks, months, and years, the motion and trajectory of the planets is just that, clockwork. We use these markers to plot out the 24 hours of a day, 365 days of a year, and the lunar cycle is, of course, intimately linked to our months. Beyond that, Newton's laws of universal gravitation, first described in 1687, allow us to this day to plot out the trajectories of all the heavenly bodies far into the future and back into the distant past. This predictability of motion is what allows us to plot great astronomical events, such as eclipses and transits, far into the future. It's why, for example, we can predict that on the 14th of September 2099, the Sun, Moon and Earth will be in precise alignment to create the final total solar eclipse of the 21st century across North America. But 100 years ahead or behind us is nothing more than a proverbial blink in terms of the life of the solar system, and over longer durations the clockwork becomes a lot less reliable. If there was only one planet orbiting one star, for example if Mercury was the orphan child of the solar system, we would be able to calculate precisely the gravitational force between Mercury and the Sun, and to plot Mercury's orbit around the Sun with essentially infinite precision. But add one more planet into our rather vacant imaginary solar system, let's say we make it Jupiter, so there is now a gravitational force between all three objects, the Sun, Mercury and Jupiter, and it's no longer possible to calculate exactly where they're all going to be in the future or where they were at some point in the past. When there are more than two objects in play at any one time, you have what physicists call a chaotic system. It means the planets can push and pull one another, moving entire orbits in ways we simply cannot predict. So the further we look back in time, the less certain we are of the position of any of the planets. Our mathematics fails, so instead we have to rely on circumstantial evidence to piece together a picture of the past. In the case of Mercury, it's the evidence from MESSENGER detailing the levels of volatile elements like potassium and sulfur that enable us to begin to understand the early life of the planet and infer that Mercury must have begun life further out in the solar system than it finds itself today. So what happened next? How did a planet that began its life in the sweet spot of the solar system end up in the scorched interior? The answer lies in the other clue MESSENGER confirmed for us, Mercury's massive iron core. Relative to its size, Mercury has the most massive core of any of the rocky planets. 75% of its diameter and almost half of its mass is molten iron, compared to around just a fifth of the mass of the Earth. We've suspected the oddity of Mercury's composition for well over 150 years, and that's because of some brilliant deduction by a German astronomer called Johann Franz Encke, who determined the mass of Mercury by measuring the gravitational effect it had on a passing comet, a comet that we now call, unsurprisingly, Comet Encke. With an approximation of the planet's mass, we are able to calculate the density of the planet, and with that calculation, approximate its composition. So we've known for some time that Mercury is odd, but only with the arrival of MESSENGER did we begin to reveal just how odd the smallest planet actually is. By accurately measuring Mercury's magnetic field, we've been able to confirm that far from being a geologically dead planet, Mercury has a dynamic magnetic field driven by an internal force, indicating that the core is at least partially liquid. This goes against the conventional thinking of planetary dynamics, because we would expect a planet as small as Mercury to have lost its internal heat long ago. Just as Mars lost its heat because of its size, we would have expected the core of Mercury to have cooled and solidified. But MESSENGER's data proved otherwise. By combining precise measurements of Mercury's gravity field with the extraordinary mapping of its surface, MESSENGER found that Mercury's structure is unique in the solar system. It appears to have a solid silicate crust and mantle above a solid layer of iron sulfide, which surrounds a deeper liquid core layer, possibly with a solid inner core at the center of the planet. This challenges all the theories about its formation. 4.5 billion years ago, we know that the inner solar system was in turmoil. In the middle of it all, the newly born Mercury found itself orbiting far out from today's intimate proximity with the Sun, surrounded by rocky debris and scores of planetary embryos all jockeying for position. The young solar system was still a place where planets could live or die. But it wasn't just the rocky planets that found themselves disturbed. Jupiter, the largest and oldest of all the planets, was on the move. And when a planet of that size shifts its position, there are almost always casualties. We'll come back to the story of Jupiter's grand tack and the havoc it spread throughout the solar system in Chapter 3. But for now, all we need to know is that the evidence suggests that the juvenile Mercury was kicked by the gravitational force of Jupiter on an inward trajectory, finding itself flung in towards the Sun and into the path of danger. In the crowded orbits of the early solar system, such a change of course was fraught with danger, and all of the evidence indicated that this was the most violent and defining of turns in Mercury's history. As the planet swerved inwards, it collided with another embryonic world and shattered. Today we see the evidence of this ferocious collision in the strange structure of this tiny planet. A giant core has been left behind, the exposed interior of a planet that had much of its outer layer, its crust mantle, stripped away and lost to space in the aftermath of the collision. This collision not only transformed the physical characteristics of the planet, but also knocked Mercury further inwards on a lopsided trajectory that we see reflected in the most elliptical orbit of all the planets. Although we cannot be certain of these events, it's a brilliant piece of scientific deduction to use the evidence we have to create a plausible scenario of events that happened unimaginably long ago. Events that drove the first rock from the Sun from a position full of potential to a place much too close to the Sun to support any form of life. An opportunity lost. After 4 years of observation and its brilliant discovery of Mercury's ancient past, Messenger finally ran out of fuel on the 30th of April 2015 and added yet another crater to this tortured world that once held such promise. Planet of Mystery. Shrouded in an unbroken blanket of cloud, the next rock from the Sun tells a very different story. Over 50 million kilometers beyond Mercury lies a world that at first sight has the potential to be far more Earth-like than her scorched inner companion. Venus is perhaps the most mysterious of all the planets. Lying on the inner edge of the so-called habitable zone, this is a planet that holds its secrets close. For centuries it has teased us with its brightness in the early morning and early evening sky. It's so bright because it's a large planet about the same size as the Earth. It's not too far away from us either, and the clouds that shroud it are highly reflective, reflecting 3/4 of the light that hits them. That's the frustrating but tantalizing thing about Venus, because even when you look at it through a big telescope, it is featureless. You never see the surface, which means that until the 1950s, scientists could only speculate about what lay beneath. In the late 19th and early 20th centuries, many thought that beneath her clouds Venus was hiding a mirror world to Earth. If not home to complex sentient life, then certainly hosting basic life forms. Faced with that impenetrable cloak, our collective imaginations fueled the idea of a living, breathing world beneath the clouds, a shroud that meant for the first half of the 20th century we lived convinced that we were far from alone in the solar system. Nobel Prize-winning chemist Svante Arrhenius was one of the most renowned scientists to fuel the mythology of what lurked behind Venus's cover. Like many of the scientists of his era, Arrhenius let his curiosity wander into many different realms, including astronomy, and he hypothesized at length about the Venusian environment. Assuming the clouds of Venus were composed of water, he wrote in his book The Destinies of the Stars that a very great part of the surface of Venus is no doubt covered with swamps, creating an environment not unlike the tropical rainforests found here on Earth. Expanding on this picture, He suggested that the complete cloud cover of the planet created a uniformity totally unlike the extremes of weather that define different parts of the Earth. In Arrhenius's imagination, this stable environment, with a consistently uniform climate all over the planet, meant that any life on Venus lived without the evolutionary pressures of changing environments that drive natural selection here on Earth, leaving Venus in an evolutionary limbo akin to the Carboniferous period. Describing a world full of prehistoric swamps and dark forests, Arrhenius created the perfect canvas for science fiction writers of the time to conjure up a menagerie of curious life forms lurking beneath the clouds. Today, Arrhenius is far less known for his fertile imaginings on the wildlife of Venus than he is for his work on the climate of Earth. In 1896, he was the first scientist to use basic principles of chemistry to demonstrate the impact that the atmosphere can have, in particular levels of carbon dioxide, on the surface temperature, a process that was called the Arrhenius effect, but is now known as the greenhouse effect, an effect that would not only have profound consequences for our understanding of our impact on our own planet, but would also be vital in explaining the true nature of Venus beneath the clouds. By the 1920s, as ground-based technology improved, we stopped painting the surface of Venus with our imaginations and started filling in the gaps with facts. The first spectroscopic analysis of the planet's atmosphere suggested that it wasn't water or oxygen that filled the clouds of Venus, so some thought this hinted at an arid desert land beneath. Others speculated that formaldehyde filled the air, leading to the belief that Venus was not only a dead planet but a pickled one too. But come the 1950s, the true nature of Venus began to be revealed, as more accurate Earth-based observations suggested the presence of overwhelming levels of one defining gas in the Venusian atmosphere. This was not a planet shrouded in clouds of water and oxygen, nor pickled in formaldehyde. This was a planet engulfed in a blanket of carbon dioxide, and as Arrhenius had demonstrated on Earth, this almost certainly meant that whatever lay beneath the clouds, the heat would be beyond the limits of even the most resilient life forms on Earth. As the first spacecraft were being built to explore our sister world, it was becoming increasingly clear that visiting Venus would be far from easy, and she would be far from welcoming. In the early 1960s, the Soviet Union began a series of missions under the program name Venera, which attempted to explore the atmosphere and surface of Venus directly for the first time. The initial launches of the Venera program failed before they had even left Earth's orbit, but within a couple of years the program began to slowly see some success. Venera 1 was successfully launched on the 12th of February 1961. Designed as a flyby mission, it is thought to have passed within 100,000 kilometers of Venus, but a total telemetry failure on the craft meant that no data was returned to Earth. As far as we know, Venera 1 is still in orbit around the Sun to this day. Venera 3 attempted to go a step further, and was designed to enter the Venusian atmosphere to take the first direct measurements. However, on crossing the atmospheric boundary, the probe's systems failed, and no data was returned as it plummeted towards the ground. All that was left for Venera 3 was the historic position as the first human-built object to crash into another planet's surface. Despite multiple failures, the Soviets didn't give up, and in October 1967, Venera 4 entered the atmosphere of Venus and sent back data supporting the Earth-based observations, revealing for the first time that the blanket of clouds surrounding Venus was made up of primarily carbon dioxide, 90 to 95%, 3% nitrogen, and just trace amounts of oxygen and water vapor. Venera 4 confirmed beyond all doubt that this was no second Earth. As it descended through the thick clouds, the temperature rose to 262 degrees Celsius. The atmospheric pressure increased to 22 standard atmospheres, 2,200 kPa, and this was still 26 kilometers above the surface. As Venera 4 parachuted its way down to the surface, it provided data to Earth while confirming its own imminent death. This was a spacecraft that was not designed to survive the intense pressures and temperatures it was measuring, let alone the lack of the water landing it was designed for. The craft failed during the descent and was lost long before it reached the surface. Gradually, through the following missions, the Soviet scientists began to overcome each and every challenge Venus put in front of them. Venera 7 was built to survive the most violent of landings, and even though its parachute failed, it made it to the surface intact in 1970 and was able to use its damaged antennae to transmit limited temperature data for 23 minutes before it expired. Venera 9 not only made it to the surface and operated for 53 minutes in October 1975, but was also the first craft to successfully deploy its camera on the ground and transmit an image back to Earth. In the first ever picture taken from the surface of another planet, the black and white fractured image revealed a rocky, desolate landscape, with measurements confirming it to be a blistering 485 degrees Celsius, with an atmospheric pressure of 90 atm crashing down. By the time Venera 13 launched on the 30th of October 1981, the ambition of the missions and the confidence in delivering data from the surface had been radically transformed. Venera 13 functioned for 127 minutes, in recorded temperatures of 457 degrees Celsius and a pressure of 89 Earth atmospheres. The probe's cameras deployed, taking the first color image from the surface of Venus. Spring-loaded arms measured the compressibility of the soil, while a mechanical drill arm took a sample of the Venusian surface that was analyzed by an onboard spectrometer. If that wasn't enough, onboard microphones were deployed to record the vicious winds that were assumed to be whipping the surface of Venus, the first ever recording of the sound of another planet. As the Venera missions came to a close in 1983, not even the smallest doubt remained of Venus's hostility. Far from the benign water world we had once imagined, the reality was that this was not a sister we recognized. In our search of the heavens for a place like home, we'd found a toxic, fiery hellscape. Venus is an enigmatic world, almost Earth-like in size, position, and potential, and yet as far from paradise as it's possible to imagine. If Mercury's story is one of catastrophic orbital change, and Earth's of balance and stability, the story of Venus is a tragedy, a tale of subtle yet relentless decline. So why did it all go wrong for Venus? Why did a world born with such similarities to the Earth take such a different path? To answer that, we need to look beyond the tortured planet we see today and go back to a time when Venus was a young, thriving planet.